So what is so special with carboxylic acid derivatives? Let's draw this general structure for carboxylic acid derivatives again. So this is the general structure of carboxylic acid derivatives. Now we write L, you can write Y, of course, where L can be X if it's an acid halide, again, as we have seen before. It could be a carboxylate as in acid anhydride, or OR as in esters, or SR as in thioesters, or NR2 in general as in amide. So what is so special with them? What's fascinating about their chemistry is actually a combination of several electronic factors. The first factor is inductive effect. Oxygen is more electronegative than carbon in this carbonyl group. So oxygen would pull electrons more in this covalent bond, leaving carbon with a positive partial charge and oxygen with a negative partial charge. So this is inductive withdrawal. And this inductive withdrawal by oxygen makes this carbon of the carbonyl group electrophilic. So we can label this as electrophilic as a result. That carbon is not only actually electrophilic because of inductive withdrawal or inductive effect, it's also electrophilic due to resonance. That carbon oxygen bond can be broken to give another resonance form, something like this. And that's a clear evidence now that carbon is electrophilic because now it has a positive charge because it has lost its electron share. So this is resonance withdrawal or resonance effect in general. And it is clear that carbon is electrophilic. Yeah. So if it is electrophilic, then it is susceptible to nucleophilic attack. And there is, or due to the presence of a multiple bond between that carbon and oxygen, carboxylic acid derivatives undergo initial addition step or initial nucleophilic addition step. But in this regard, they are not actually different from aldehydes and ketones. We have seen the similar effects, inductive effect and resonance in the case of aldehydes and ketones. And that's exactly why aldehydes and ketones undergo nucleophilic addition reactions. Now we see this again in carboxylic acid derivatives. So they undergo an initial nucleophilic addition step, but that's not the whole story. The difference really lies here in L or Y, if you like, in this group, what makes these compounds derivatives of carboxylic acids. Now L is a leaving group, or at least a potential leaving group, and that's a significant difference between carboxylic acid derivatives on one hand and aldehydes and ketones on the other. All of these carbonyl compounds undergo initial, if you like, nucleophilic addition step, but carboxylic acid derivatives take another step, as we will see very shortly. Let's draw the structure of carboxylic acid derivatives. Again, when a nucleophile approaches a carboxylic acid derivative, it attacks that carbon with simultaneous breakage of the carbon-oxygen double bond. So we can show this with Cayley arrows. So the nucleophile attacks that electrophilic carbon. Again, that carbon is electrophilic due to inductive effect and resonance. The carbon-oxygen double bond is simultaneously broken. That's why the intermediate, as a result of this nucleophilic addition step, and it is nucleophilic addition step because the nucleophile attacks a carbon, an electrophilic carbon of a multiple bond, double or triple. That's nucleophilic addition. This is nucleophilic addition reaction so far, if you like, or nucleophilic addition step so far. And that's so far not really different from the chemistry of aldehydes and ketones, from nucleophilic addition reactions of aldehydes and ketones. But the difference between the chemistry of aldehydes and ketones on one hand and the chemistry of carboxylic acid derivatives on the other is actually on this intermediate. Now, in the case of aldehydes and ketones, this alkoxide intermediates undergo subsequent protonation step. That's by reacting the alkoxide with an acid. But now here we have L or Y, if you like. This could be X again, as in the case of acid halides. It could be a carboxylate, as in the case of acid anhydrides, OR in esters, or NR2 in amides. This L, or potential leaving group, can actually now leave as a result of reformation of the carbonyl group, which would act as the driving force for the departure of this leaving or potential leaving group. So we can show this using Cayley arrows. As such, the carbonyl group is reformed and L leaves. So that's really the significant difference between the chemistry of aldehydes and ketones and the chemistry of carboxylic acid derivatives. Let's write the product. So the product is another or a new carbonyl compound actually, but now with a nucleophile. So it's another carbonyl compound. If you like, this step involves elimination, if you like, or departure of the leaving group. So we can describe it as elimination of the leaving group. So initial addition step, initial nucleophilic addition step, that's usual, that's normal, just like in the chemistry of aldehydes and ketones. But this is where the difference is. Due to the presence of a leaving group or a potential leaving group, now that leaving group or potential leaving group can be expelled by the reformation, by the carbonyl group, by the reformation of the carbonyl group. Now, we did not see this before in the case of aldehydes and ketones. That's because in the case of aldehydes and ketones, this L was hydrogen or R, and of course these are very poor leaving group. The result is another carbonyl compound. Overall, it is addition. It is a nucleophilic addition, which is done by the nucleophile on the carboxylic acid derivative. Overall, it's also a substitution because the nucleophile has substituted L in the carboxylic acid derivatives. Therefore, this reaction is called nucleophilic acyl substitution reaction because it's a nucleophilic addition reaction on the acyl unit or the carbonyl unit. That's an acyl unit. It's also substitution because the nucleophile overall has substituted L. So this wraps it up really. Carboxylic acid derivatives undergo nucleophilic acyl substitution reactions, whereas aldehydes and ketones undergo nucleophilic addition reactions. The difference between the two classes of compounds is really in this alkoxide intermediate. The alkoxide in the case of aldehydes and ketones undergoes protonation, whereas here in the case of carboxylic acid derivatives, it undergoes elimination. So addition followed by elimination. Overall, it's nucleophilic acyl substitution reaction.